Hi everyone. Today let's talk about section 12.9, Lagrange multipliers. Let's look at the following example. Suppose we want to find the absolute maximum and minimum values of f. On the circle x squared plus y squared equals 1. In other words, we want to optimize f subject to the constraint g of xy equals 1, where the g equals x squared plus y squared. For example, the function f may represent the temperature at the point xy in the xy plane. Therefore, optimizing f subject to the constraint g of xy equals to 1 means that we are looking for the hottest and coldest points on the unit circle. So the following figure shows the constraints, which is the fixed circles and some level sets of f. So because f equals 3y minus x, so for a level set, let's let it be a constant c. Then this is a linear equation, so they are parallel lines. So here the level sets of f are labeled with their corresponding levels. So these lines are the level sets. So based on the figure, let's answer the following questions. A. Are there any points xy on the constraint at which f of xy equals 4? Well, we're looking at 4. So 4 is this line. Do we have some points on the constraint? You can see this line do not intersect the circle, right? So no. Because no intersection with the circle, which is the constraint. Part B, are there any points on the constraint at which f of xy equals 2? Well, 2 is right here. So yes, we have this point and this point. Yes. So here we have 2 points. Part C. Are there any points on the constraint at which f of xy equals minus 5? No. Right? It's too far away. So no. Next. Are there any points xy on the constraint at which f of xy equals minus 3? You can see no intersection, so the answer is still no. Give an estimate for the maximum and minimum values for f of xy on the constraint. So depends on the picture. So let's look at the picture. Maximum, we know the up direction is more like maximum values of f, and then the bottom direction is more like smaller values of f, right? So you can see the, let me use a different color. So we can see the highest value is somewhere between 3 and 4. So I would say the maximum value is around like 3.1 or 3.2, right? Maybe more close to 3.2. We just estimate. We just look at the picture to estimate. How about the minimum value? So this point is the max. How about the minimum value? Well, depends on the picture. It looks like it's minus 1 point something, 1.2 or 1.3. So probably negative 1.3 or 1.2. Doesn't matter. We just want to estimate. So from the picture we can tell that. Alright, let's continue. Label in the figure above the approximate location where f attains its maximum and minimum values on the constraint. So, we already label it, right? And what is the geometric relation between the constraint curve and the level set of of f at the point we found? And so what can you say? You see the tangent line here. What can you say about the tangent line? The tangent line parallel to the level curve, right? Okay, see the tangent line are parallel, so we can see the tangent line of the constraints is parallel to the level set. So, i.e., okay, they have the same normal vector, right? So that means normal vector of f kind of, maybe not, we don't say the same. We should say that the normal vector of them are parallel. Okay. All right. So but we can also say they have the same normal vector because we can find one vector that are non-normal to both of them. Okay, so we know normal vectors is not unique. Given a surface, there could be many normal vectors. Okay, but in the two-dimensional, the unit normal vector, there are only two, right? Either this guy or this guy, because the unit vector, the magnitude has to be 1. So that's why we have two choices. But in general, normal vector, this is normal vector, this is normal vector, this is normal vectors. So far, so good, everybody. Okay, let's continue. So what is the geometric relation between the direction of gradient of f and gradient of g at the maximum and minimum points? Wow, do you remember the gradient of f is perpendicular to the level set of the function? Okay, so that's why here we have gradient of f, and here we have the gradient of g. So what's the relation between them? Gradient of f is parallel to the gradient of g. And furthermore, what can we say? They are constant multiple of each other. So this is lambda, okay? This is lambda. We maybe you ask, why don't we use k? Why do we need to use a Greek letter lambda? This is special about the Lagrange multiplier. The notation, we will use lambda in this case. So this is multiple of each other. Okay. What is the system of equation we would need to solve in order to find the maximum and minimum points? Okay, so first, at those points, we know that the gradient of f is a multiple of the gradient g, right? And also, those points is on the constraint. So g of xy equals to 1. This was the constraint. Okay, everybody? So we have a system of two equations, and we have two unknowns. The point is x, y, right? So the two equations, two unknown, we should be able to solve it. Okay, so the system in this part I is called the Lagrange system. The scalar lambda is called the Lagrange multiplier. Set up and solve the Lagrange system for xy. We usually don't need to solve for lambda, though we do need to check that there is a value lambda that works for our values x and y. Okay. And when we find xy, confirm our estimates from parts E and F. Okay, let's see. So F equals 3y minus x, g equals x squared plus y squared equals to 1 is the constraint, right? And so what is the gradient of f? Derivative with respect to x is minus 1. Derivative with respect to y is 3, right? Oh, okay, let's continue. So gradient of g, okay, derivative with respect to x is 2x, derivative with respect to y is 2y. Okay, so we have gradient of f equals lambda times gradient of g. So actually this is a vector value function. So I said there are two equations, not really, because here we are, so we have gradient of f and gradient g. They are functions from R2 to R2. Then compared to the coordinate functions, we actually can get two equations out of them. So here together we have three equations. And we have three unknown. Okay, they are x, y, and lambda. Okay, so in this case, minus 1, 3 equals lambda times 2x and 2y. So let's look at each coordinate function. We have minus 1 equals lambda times 2x. 3 equals lambda times 2y. And don't forget we have the constraint x squared plus y squared equals 1. Alright, and how do we do it? We can use substitution. You see here, one way is we can solve x in terms of lambda, and we can solve y in terms of lambda, and then we can plug into the equation, and then we can get an equation about lambda. And then after we solve lambda, we can plug in and find x and y again. Okay, so another way is we can eliminate lambda by using equation equation 2 divided by equation 1. Then we have 3 over minus 1 is minus 3. And then lambda cancel, 2 cancel. We have y over x. Is that okay? So that's the same as y equals negative 3x. Now we can plug in equation 3 because then x squared, y squared is 9x squared equals 1. So 10x squared equals 1, x squared equals 1 over 10, x equals plus or minus 1 over square root of 10. And then y will be negative 3 times x. So it was plus minus, then the y will be minus plus 3 over square root of 10. Okay, because it's this negative, so they're of different sign. Okay, that means if x is positive 1 over root 10, then my y is negative 3 over root 10. If my x is negative 1 over root 10, then our y will be positive 3 over root 10. We get 2 points, great. One should be the maximum, one should be the minimum. But which is which? So the Lagrange system can only help us to find some solution, okay? But the solution, some points in our solution might be the maximum, some points of our solution might be the minimum, and it is also possible that some points in our solution is neither maximum nor minimum. Okay, so it's all possible. How do we check whether they are maximum or minimum? Plug in the f. Okay, so plug in the f of 1 over root 10, negative 3 over root 10. So 3y will be negative 9 over root 10 minus x minus 1 over root 10. Well, that is minus 10 over root 10. That is minus square root of 10. And then f of minus root 10 and 3 over root 10 would be 3y. So 9 over root 10 minus minus become plus. So this is root 10. Okay, now we see this is actually minimum. Okay, and this guy is actually maximum. So far so good, everybody? Okay, and let's see. So what is this guy? So 1 over root 10 is approximately okay, sorry. So root 10 is approximately 3.16. So this is approximately negative 3.16. So let's check our answer. Oh, okay. Let's look at this. I think this graph is more accurate to this graph. This at some point when I copy this images, the number gets shifted. So this is not accurate. Okay, let me see how can I fix it. Oh, those, so you see those numbers? Okay. Sorry. Let me, so this is the, oh, okay, I know why. Okay, when I copy down the picture, so, okay, here, here the number is accurate, but there the number is not. So let me see. Let me print screen of this picture and let me try to paste it here. Can I do that? Oh, where is it? Is it here? Oh, okay. And then let me move it on top. Okay. then it's on top of everything. Okay, so let me fix the arrows. Okay, so what is get fixed? At 4 still no. At f equals to 2, we still have 2 points. And negative 5 still no intersection. But at negative 3, we actually has 2 points. So sorry. Yes, 2 points. Our graph was not so accurate. Okay, sorry about that. And now look at the picture. What is the maximum value? What's the minimum value? So we see is this point. Oh, I should use. Let me use a different color. Okay, let's use this one. You can see this point is the maximum. It's around 3.1 and 3.2. So maybe let's say 3.2. And you can see this guy is around negative 3.2. Right? Now our answer match because at the end when we solve for it, when we solve for it, we get the minimum value is negative 3.16 about, okay, and the maximum value is about positive 3.16. So that's close to 3.2. So our graph match now. Okay, so far so good, everybody. Okay, let's summarize. So the method of Lagrange multipliers in two variables. Let the objective function f and the constraint function g be differentiable on the region in R2 with the gradient of g is not 0 on the curve. This is the level set, okay? We can always say like g equal to 0 because whatever equation you have, you can just define your g to be the left hand side minus the right hand side, and then your the constraint function, the equations is associated to this curve g equal to 0. To locate the maximum and minimum values of f subject to the constraint g equals 0, carry out the following steps. First, find the values of x, y, and lambda if they exist. And that satisfies the equations. Okay, so it looks like 2 equations, but there are more because these guys are vectors. Okay, so if we have a vector in R2, then this one equation will contain we will get 2 equations, 2 coordinates. Okay, each coordinate will give us an equation. So altogether we get 3 equations. If the gradient of f and gradient of g is a vector in R3, then we have 3 coordinate function. Well, then this vector equation will give us 3 scalar equations. Okay? So yeah, we will see more example. So among the values we found in step 1, select the largest and smallest f values, which are maximum and minimum values of f, subject to the constraint g. Okay, so we might find many values, maybe 5 of them, and then you evaluate f of those points, and then you pick the largest to be the maximum, pick the smallest to be the minimum, and then the rest, they are neither maximum nor minimum. So far so good, everybody? All right. Let's continue. Suppose we want to find the absolute maximum and minimum values of f equals y minus x squared. On the circle, x squared plus y squared equals 1. In other words, we want to optimize f subject to the constraint g equals 1, where g equals x squared plus y squared. So here, if we define g of xy equals x squared plus y squared minus 1, then the x squared plus y squared equals to 1 is correspond to the levels the level curve g equal to 0. Okay, that's what it means, that you can always let your g be your left hand side minus the right hand side. Okay, so the following figure shows the constraints, the fixed circle, and some level sets of f, the parabolas. The level sets of f are labeled with their corresponding levels. Okay, let's see here. I think there's something wrong with this picture. Okay, this picture is correct. Okay, let me, yes. I don't know why is that. Maybe when I copy it and then the image shifts to this. So let me copy again. Where is it? Oh. So okay, is my picture here? Where is it? Okay. Oh. So, okay. Let me shift here. Okay. Alright, let's answer the following questions. Are there any points x, y on the constraint at which f equals minus 1? Where? Oh. Okay. So I think somehow they okay, in my original picture we have more parabola going down like this. Sorry, didn't draw it nicely. Okay, so there are more parabolas down there. Okay. Okay, alright. Alright. Okay. So let's start. Where is it? Here. Okay. Alright, so minus 1 is right here. Okay, this is minus 1. And are there any points on the constraint at which f equals minus 1? Yes. How many points? We have this guy, and this guy. So 3 points. Yes. So yes, and there are 3 points. Are there any points at minus 1.5? Minus 1.5 is here. No. No points. No intersection. Are there any points on the constraint at which f of xy is less than minus 1? Yes, it is. There is. So they are okay. They are these pieces and these pieces, right? So we know those values is less than minus 1, but it's bigger than minus 1.5. Okay? Label the approximate location where f attains its maximum and minimum values on the constraint. So, what do you say? Okay, what do you say? Which one is the biggest? This one would be the biggest, and we can see it's 1, right? How about the smallest? I would say some points here and another points there, right? They would be the minimum. This guy would be the maximum. And so label in the figure to the right the approximate location of our solutions to the Lagrange system. Okay, so we say this is the maximum and this is the minimum. So they would be the solution to the Lagrange system, right? And you can see gradient of f is like here, gradient of g is like there, right? Are your answer in part D and E the same? Oh, so let's gonna solve, okay? Solve this system. So let's solve the system. F is y minus x squared. G equals x squared plus y squared equals 1 is the constraint. So gradient of f is the derivative with respect to x minus 2x. The derivative with respect to y is 1. Gradient of g, derivative with respect to x, 2x, derivative with respect to y, 2y. So we have gradient of f equals, oh, okay, so it's this system, right? And then we will have minus 2x1 equals lambda 2x 2y. Okay, this is the same as saying minus 2x equals lambda times 2x. 1 equals lambda times 2y. And don't forget our constraint. So this is the 3 equations. We have 3 unknowns. And let's look at the first equation. You see? When we move here, even though you see 2x on both sides, you cannot divide it by x. If you divide it by x, you assume x is not 0, so you will lose a solution. So what you do is you move everything on one side. Let's move the 2x to on the right. So you have lambda 2x plus 2x equal to 0. Factor out 2x, we have lambda plus 1 equal to 0. This means x is 0 or lambda plus 1 is 0, so lambda equals minus 1. Okay, so this, by looking at the first equation, it gives us 2 cases. So now let's continue. If, let me use this case 1. If x equal to 0, then you can see equation has no x, so we plug in equation 3. Then we get 0 plus y squared equals 1, so y equals plus or minus 1. So far so good. Then we have 0, 1 and 0, minus 1. So we get 2 points here. If lambda equals minus 1, then which remaining two equation has lambda. The equation 2 has lambda. Then y equals 1 over 2 lambda, but lambda equals -1, so -1 over 2. Then we have the y, we plug in 3 to find x. X squared plus y squared is 1 over 4 equals 1. X squared is 1 minus 1 over 4 is 3 over 4. X equals plus or minus root 3 over 2. So we have 2 points, root 3 over 2, and y is -1/2. So far, so good. And you can see from the picture, this guy is root 3 over 2 minus 1/2. This guy is minus root 3 over 2 and minus 1/2. And they are the minimum. And 0, 1, so this is 0, 1. That is the maximum. But we also have 0, -1. This is neither. Okay, so now all the solution of this Lagrange system will be a maximum or minimum. It could be neither. And we can check from plotting into f. So f of 0, 1, we get y is 1. 1 minus x squared, 1 minus 0 is 1. F of 0 minus 1, y is -1, minus 0 is -1. F of root 3 over 2 minus 1/2, y would be -1/2 minus x squared, which is 3 over 4. This is common denominator 4, and then that is like 2 over 4. Okay, so that's 5 over 4. And we know that if we plug in root 3 over negative root 3 over 2, oh, I forgot that. So we also have negative root 3 over 2 and -1/2. So negative root 3 over 2 minus 1/2 will give us the same answer. So that's why both of them are minimum. And this guy is maximum. And this guy is neither. Okay, so yeah, so our answer in part D and F are the same. So far, so good, everybody. Good, let's continue. So I just want to point out one more thing here. So here, be careful. Don't divide by 2x on both sides. Okay, you might lose, okay, because we might lose the solution x equal to 0. Okay, because you can divide by a constant, but you cannot divide by a variable. Okay, so the correct way is move all the terms on one side, then factor it. Okay, all right, let's continue. Okay, so here we have f. We want to optimize f subject to the constraint y plus 2x equals 3. Let's get back to our color. Okay, so Lagrange system, keep those in mind. Here, what is g? We can define g to be the left-hand side minus the right-hand side. All right, then what is gradient of f? Derivative with respect to x is 2x. Derivative with respect to y is 2y. Okay. And here, oh, so do you see this example is kind of, you remember our first example, we have the circle is the constraint and then this is the level set. Well, this example is the opposite. We have the level set being the circles and then the constraint is a line. Well, this line is correspond to y equals 3 minus 2x. So Okay, so negative slope, so going down, right? So it's like this. Okay. So this is the constraint. So this is the constraint, and we want to have the constraint. Which one is the maximum? You can see this is the maximum, and probably this guy is the minimum, and then this guy and this guy is the maximum. Okay, so you can see, just keep in mind F and G. Which one is the level curves? Which one is the constraint? Okay. So constraint, you only have one curve. Okay, the F, you have different values, so you have a level curves. Okay, so gradient of G, partial F, partial G, partial X is 2, and then derivative with respect to Y is 1. Okay, then let's set it up. So gradient of F equals lambda gradient of G, and then G equal to 0. So if you define your G by using the left hand side minus the right hand side, then this guy is always G equal to 0. So that will give us 2x equals lambda times 2, 2y equals lambda times 1, and G, so y plus 2x minus 3 equals 0. Okay, so here, well, one way is we use equation 1 and equation 2. We can solve x in terms of lambda, solve y in terms of lambda, and then plot those lambdas into equation 3. We get equation about lambda, and then we can find lambda values, and then plug it back to find x and y. And then, but what I would do is I will eliminate lambda. Okay, so I use equation 1 over equation 2, or we can use equation 2 over equation 1. But in this process, you want to avoid fraction. So you use equation 2 over equation 1, you will get 1/2. So that's not what we want. So I strongly recommend you during this calculation, try to avoid fraction if we're able to. Okay, 1 divided by 2, so 2 cancel, x over y on the left, none cancel, and we have 2 over 1 is 2, okay? So that's the same as x equals 2y, so we plug in 3, y plus 2x become 4y minus 3 equals 0. Let's see. So here we got 5y equals 3, y equals 3 over 5. Okay, and then what is x? X is 2 times y, so x is gonna be 6 over 5. So we get 6 over 5 over 3 over 5. So we only get one solution. So what is wrong? You know what? The level curve, there could be infinite many circles. So there's no maximum at all. Oops. Okay, there is no maximum at all. There's only minimum, because we can have more and more circle. Sorry about that, I didn't draw more enough circle. Okay, so this is also an example to tell you that we might make mistakes. So please check your answer carefully. And you can see at the end, we get only 1 point. So then we go back and check our words, and then we realize, oh, there's no maximum. So from the picture, we can see no maximum, and then this guy would be the minimum. But we also need to test that. So plug this number into f. So that f of 6 over 5, 3 over 5 is 6 square over 5 square plus 3 square over 5 square. So the common denominator is the same. 36 plus 9 is 45, right? Over 5 square. Oh, that's 9 over 5. So far, so good, everybody. And this is this is the minimum we can see from the picture, and you can see when we pick the points that is far away, then it will be larger. So it's going to be a larger number. So far so good, everybody. You can also like randomly choose another point on the line and plug in f to see whether that number is bigger than 9/5. Let's see we pick x equals to 1, and then y equals 3 minus 2x will be 3 minus 2. Oh, 1 is a number, right? So f of 1 will be 1 squared plus 1 squared, which is 2. You can see 2 is larger than 9/5. You can pick some random points, and you will see the number is always greater than 9/5. So far so good, everybody. All right, let's continue. Okay, so let's continue in video part B, okay? Because I'm going to talk about Lagrange multiplier in 3 variables instead of 2 variables. So kind of generalize the idea to 1 more dimension. See you soon!